Russ Chianelli from Texas, at Pasadena. He's going to be sharing with us some studies on the fundamental properties of transition metal sulfide.
Well, John, I'm really happy to be here today because when I left Brooklyn Polytech, the late Ephraim Banks said to me, well, you're going to Exxon, you're going to work in catalysis. And I said, oh, no, I'm not going to work in catalysis. I'm going to work on new energy and all of those new things. And he said, well, there's a guy over there named John Sinfeld, and I think you can learn a lot from him. So I came over and started working on the battery cathodes and so on, and I began to talk to John a little bit, and I don't know if you remember those conversations, but he was very patient with the questions, and little by little I got hooked on catalysis. And the questions that were raised over studying catalysis for many years now are questions that I heard discussed today that are just fascinating, and the first time they were raised were discussions with John. So I want to thank you for that, John, and say that you really did a couple of things for us. Not only did you show us how to do the research, and I hope to illustrate that quickly in my talk here, but you also made the environment for us. You know, there was a lot of people in this room I'm glad to see, and we were always lucky because John sort of protected the environment and said, let these guys, you know, do their thing. And so I feel very lucky to have been there with John and the other people, and also very lucky to be able to study the systems the way we studied them in a very fundamental way, and I don't think we could have done that without you. Of course, what I'm talking about are transition metal sulfide catalysts, which are HDS catalysts. And what you didn't tell me, John, was that if you take sulfur out of the feed, nobody will pay any more for it. And therefore, it's environmental catalysis, and it doesn't make a lot more per barrel. And so you didn't tell me that. On the other hand, it has allowed me to say over the years that I've been an environmental scientist for 20 years. Anyway, when we started, I was making battery cathodes in materials like titanium disulfide. And we're going to have some recycled knowledge here again. And I was working with Terry Pecoraro, who some of you may remember. And Terry picked the model reaction as dibenzothiophenone. And at the time, there was a lot of argument about whether you can use a model compound. You have to run everything on real feeds and so on. So, well, we overcame that, and with time, what I can tell you today is that the dibenzothiophenone reaction, particularly if you go into the substituted forms, is a very accurate predictor for real feed behavior. And you can save an awful lot of money, and you can learn some very fundamental things about the catalyst if you use a model compound like that. Anyway, I began to give Terry some of these materials like titanium and zirconium disulfide, and she was measuring them, and she said, you know, those are pretty bad, they really are terrible, why don't you try again? And so I gave her some niobium and vanadium and tantalum sulfides, and she said, you know, if you give me any more catalysts like that, that's it. So we moved on and made some molybdenum sulfide and chromium and tungsten sulfide, and they were somewhat better. And she said, well, yeah, but we knew that. So we went on, and we made rhenium disulfide. And she said, well, now that's getting quite a bit better. And we had a debate about whether we should stop there and work on that or not. And also an argument about whether what we should do about technetium. And I actually bought a gram of technetium ammonium pertechnate. And then my technician got pregnant because it's radioactive. And they said, no, you can't run that. So, my friends. Anyway, we didn't run magnesium disulfide. But there is a patent by the Atomic Energy Commission in about 1965 that says technetium disulfide is a very good hydrodesulfurization catalyst. So anyway, I think actually, John, if you weren't there, we might have stopped here, okay? But we pushed on, and of course, many of you have seen this volcano plot with ruthenium sulfide on the top. And this plot has become measured many different ways. Many different groups have measured it right now on real feeds, different reactions, and so forth. And this plot has appeared in the latest version of Thomas and Thomas. So it turns out to be kind of the fundamental Ten Commandments of sulfide catalysis. And yet at the time when we looked at it, it said, well, it looks very much like the plots, ethane hydrogenolysis plots that we saw before. And yet each one of these is alloyed with sulfur. And it was very puzzling to us looking at John's work that in a different reaction you should get essentially the same results. In this particular case, the first row transition metals are even more well separated from the 4D and 5D electrons, second and third row transition metals. And we read John's papers and so on. We had arguments about Sabatier effect and so on, and how this was really what we call the Goldilocks effect. Okay, these sites are too hot, these sites are too cold, these sites are just right. And it turns out too that if you take falling percent D character in this case, you get an absolutely perfect correlation. So this tells us in another way the importance of these 4 and 5D electrons. And I think that's something that we need to remember again as we recycle some of this knowledge. Now, and I want to say also that this is becoming very timely again. As an environmental scientist, the problem in many air sheds in the country is sulfur, no doubt about it. And the oil companies themselves are looking for better catalysts than the commercial catalysts that they have. And one of the frustrations about this plot is I guarantee you that if you fill your reactor with ruthenium sulfide, you will see a result that you cannot achieve with any known commercial catalyst, unless maybe you have 10 reactors in a row. And at the same time, having said that, it has proven extraordinarily difficult to support. So it remains a challenge for those of us chemists, physicists, catalyst people to try to understand these results and to take advantage of the knowledge that we have here. Because of the fact that the desulfurization is again taking on an important meaning in refining, there's a lot of interest in trying to understand this effect. As a matter of fact, there is a conference that's going to take place in a few weeks, a NATO conference in Budapest that's going to talk about some of this. And in about the mid-'80s or so on, a theoretician by the name of Suzanne Harris and myself began to see if we could ask some questions that were a little bit deeper than falling percent D character and so forth. So we did a series of X-alpha calculations in which we assumed that the metal was in an octahedral site, and we calculated the molecular orbitals, schematically shown here, 3p, 3s, and the highest antibonding orbitals, which are filled with d electrons. I might point out in some of the discussion that Keith Lowell had before, these are semiconductors, most of them. And in that sense, they're sort of easier to study. And we did these calculations, and we worried a lot about the number of sites and the quality of the sites. And we basically came to the conclusion that the quality of the site was something called an activity parameter, which is the number of electrons in this pi-bonding anti-orbital, and something about the covalency, the tendency for them to covalently bond. And as I said, this was all published in a series of papers in about '86. Now these calculations, which I'll just show you a little more schematically in a moment, they didn't really tell us anything more than 4 and 5d electrons are important. But the one thing that was really interesting to us when we did this was that the commercial systems are combinations of cobalt molybdenum and nickel molybdenum, as you all know. And we were able to hypothesize that at the surface of the active catalysts were places where sulfurs were shared by cobalt and molybdenum. And then we calculated in the same way the electronic structure of those clusters that were on the surface. And what we found was that we could predict the electronic structure of the promoted system, and they fit into the general scheme that we had worked out for the simple sulfides. And so we put them all together. And it's fairly complicated to see the whole thing, but if you look at these green things, which represent the 3 p electrons here, and the blue things above, which represent the antibody orbitals up here, you see as we go through the normal metals, niobium, molybdenum, rhenium, ruthenium, rhodium, palladium, rhenium being a surrogate for technetium. No more comments, Gary, on technetium. You see that these antibody orbitals are moving closer until they submerge into 3p band here, and they're progressively being filled with electrons. So the ruthenium disulfide, remember these are all sulfides, has 6 electrons in that antibody orbital up there. And in fact, if you look at UPS or other ways of measuring that electron density, switch over to the band language, in the gap at the Fermi level, you see that ruthenium sulfide has this huge electron density, right where you would expect it. And some of you point out, well, no holes. But remember, one of the things we did in these calculations was simply to calculate the electronic structure of the bulk material. And we assumed that the bulk material would form the basis, as you were, for the surface states. And when we did this, we didn't say anything about the surface states. And I'm glad we didn't, as you'll see at the end of the talk, say anything about that. And we took a lot of heat at the time because we're doing a whole set of calculations and correlating it to activity. Now, of course, you can do these calculations much more easily than we could in that period of time. But the correlations were pretty good, and this is coming back in interest again, too, because you can see when you mix the cobalt and molybdenum, if you look at the whole scheme, you have the antibody orbitals of molybdenum, 2 electrons in it, and the 3D manifold of the other promoting is coming down and eventually burying itself underneath these molybdenum levels, which stay in the same spot. So at iron, we have 2 electrons in the molybdenum antibody orbitals and the 6 iron orbitals under it, and it behaves just like molybdenum disulfide. When you move over 1 to cobalt, there's 1 extra electron above it, and it falls down into the molybdenum levels, and it makes the promoted system look just like rhenium, and that's in fact the way it behaves. If you go over to nickel, there are 2 up there, they fall down, and it behaves as an element that doesn't exist, actually. And of course, the D5 is missing. When you go over to copper, it's all of these levels, the 3D manifolds now below, and it takes 1 electron away from the molybdenum and makes it look like niobium, and it deactivates it. So we were very happy about this scheme, and as I said, right now in a couple of weeks in Europe, there'll be a big argument about all of this. And the reason is, not only do we want to understand the fundamentals, but you can see that there's some missing elements in here. That it's possible that by using some of these models, that the electronic programs that we're using now, that we might be able to predict some new catalyst configurations and so on. And I think that's where you're going to see that going next. Nevertheless, it's one example where we think that the ability to use these, have a very fundamental approach that John would encourage, and to use computer calculations in combination with experiment is really something very active right now in lots of areas of catalysis. But, and this takes us to the next level of sort of complexity here, it turns out that these systems are much more difficult to describe than metals. Here's the periodic table, and you can see that the structures of all these materials are quite different. Pyrite structure for ruthenium sulfide, the most active. Delayed structure for molybdenum sulfide. Amorphous structures down here. And I think this is a very important point that perhaps in the future we ought to think of these trends, electronic trends and so on, not so much as metals, sulfides, oxides, and so on, but rather to use something that's kind of a catchy phrase, the sites and phases self-assemble in the feed, with the 4 and 5d electrons being the most important factor. And so that's why in some cases, if you have a carbide, it will behave like a metal because the carbide is a stable state. And there's intermediate cases, which I'm going to show you in a minute, where reminiscent of the SMSI effect, where the bulk phase is stable in the X-ray, but the surface phase is different. And I think that's one of the points that's been missed here in the sulfide catalysis, as I'll try to indicate. So we went on, and the other thing I would like to make is that I think that in terms of these catalysts, we're finished with aluminum-supported catalysts in terms of more activity improvement that we can get. They're already spewing off metals as the metal concentration gets higher. So that the next generation of catalysts in this field are going to be what I call nanoparticle catalysts. And that is catalysts that spread the metal out in some other way, maybe like Terry Baker was talking about before. So this, again, we'll take a page from what John taught us. We wanted to look at a little bit at, now that we understand, which I will call the electronic effect, and we had many arguments about that. As the basic principle, we want to look at some of the specifics of the structures. This is ruthenium disulfide structure. It's kind of unique in the sulfides, and it has these dicalcogen bonds like this. And it's fairly well behaved. We might call it structure insensitive as far as we know. This is a crystal which is, I don't know, maybe 20 microns across. Lots of nice faces on it like this. But it's well behaved in the sense that as you make the particles smaller, you just get linear relations to chemisorption and so on and so forth. And one of the other things about that I always admired about your work, John, was I remember when I first realized that you were working with XFs. And I thought that was so far from, and the NMR with Charlie Slichter, I thought that was so far from where I thought you were doing. It was a big jump. And what I learned from that was that we should try to apply the latest techniques to understanding these problems. And in one recent work here, my last postdoc at Exxon cleaved this crystal, not that one, but one like it, and began to do AFM and STM studies on it. Now, one of the things about sulfides is they're very difficult to study in high vacuum. If you put them in high vacuum and try to do normal techniques on it, the surfaces fall apart, sulfur pumps out of it. If you try to sulfide a metal single crystal, you get an amorphous mess. So you need some new techniques, and it turns out that if you do AFM, STM work, and this work is done with me by Steve Kelty, just leave it in air. And the pyrite surface structure will immediately relax into a structure that looks like this. No, it's not oxidation, it's not garbage, it's a very ordered structure reflecting the ability of these d electrons that are up there to rearrange themselves, no matter what environment they're in. And we're studying that right now, and I don't know exactly what this structure is. We have a paper that we're arguing with the referees about it right now, so that we should have it settled in a little while. But I want to say something about it. This is an image. This is an STM image. And you can bias the voltage. And if you have voltage at one point, I'll show this one. Okay, when you're getting the electrons to come out into the tip, you're getting them from the valence band. And when you're forcing them in at a different voltage, you're filling the conduction band. So you're getting maps of these different bands when you look at an image like that. Okay. And furthermore, in this system, when you do cleave it, you see a third set of images at almost zero voltage here when you do the analysis. And then what we're looking at there are what we would call dangling bonds that are in the band gap. So we're looking directly at what may be the catalytic sites. This is work, as he said, trying to bring in some new tools. When you use AFM, STM, you can run the AFM virtually in any environment. And then you combine that with a theoretical approach to model the surfaces. And finally, I just want to say that the other system, of course, is the layered sulfide system. Structure shown here, anisotropic structure. And people like Sam Tauster firstly showed that the active sites are on the edges by chemisorption. And that these planes are basically inert. This is completely opposite from what we were looking at with ruthenium sulfide. Here's a picture of a crystal. Again, these are the active planes here. These are inert, we thought. Okay? And what you want to do to make these more active is just to reduce the radius of these things so you get more edge area. So the total activity will be a result of reducing the edge area there. You can see the interaction of these edges in many ways. You can see that these are steps that have more edges, and metals, like promoted metals, will interact with these edges. And so we spent some time studying the reactivity of these edges with both metals and with chemisorption and so on, and the reactivity. One of the more interesting things that we found, which I think is unique in catalysis, is that the way the crystal is stacked, which you can easily determine from X-ray diffraction by measuring the stack reflection in this direction, will determine the way these two primary products go. The more you have catalyst stacked, assuming that the gold edge area is constant, the more of this product you get. And if you destack it down to single layers, you'll get more of this product. So you can control the selectivity of this reaction just by stacking and destacking these systems like that. Now, when we put this in the literature, we knew that this was correct because we made some catalysts based upon this principle. For example, this is a single layers on iron sulfide support. This catalyst is extremely selective to hydrogenation and very stable. The current papers are now pretty much convinced that this model, which we call the rim edge model, is correct. And now that's kind of an unusual thing in catalysis, and I don't know what to call it. Call it a sensitive structure, insensitive reaction, because we don't think that any of the sites are changing, just being covered and uncovered by the stacking and destacking process that we've been doing. Now, finally, I want to end in the next few minutes by saying that there is something I think that has been missed in this sulfide catalysis in the last 20 years that is going to make some points fairly clear. And that is, people have been ignoring the role of carbon. If you make some molybdenum sulfide catalyst by decomposing this compound, you will always get molybdenum sulfide plus X. And X, you can drive it out and crystallize the material by heating up the catalyst. This X is replaced in the reactor by carbon. And it's not coke, it's covalently bound carbon. We will shortly present some synchrotron studies that confirm this. So that many of these sulfides, ruthenium sulfide, and this is a schematic of it, and molybdenum sulfide go through this process in the reactor where the excess sulfur on the surface, which is dependent upon the surface area or the edge area, in the case of molybdenum, is replaced by carbide in the reactor. And that means that these materials are sulfide-supported carbides. Those are the active phases. I'm very happy that when we did the original trends, we didn't say too much about what was on the surface. The same thing is true of the ruthenium sulfide. It's very easy to convince yourself that the particles that I showed before in the active state are carbide on the surface. You can show the reaction of these materials with carbon at room temperature. And finally, I want to say that this is also true for, I'll just say it, for the cobalt-promoted phases. That the cobalt-promoted phases are really a two-phase system. This is another point I think that's been missed in the literature. Somebody said it looks like the French flag, but it's a phase diagram which just shows that as you add cobalt to the system, you go up the promotion curve, then you get to some region where there are two phases, then you go down back to the activity of the cobalt, pure cobalt phase and pure molybdenum phase. So it's a known fact that you can start with cobalt-9S8 and add molybdenum to it, and you will go up the promotion curve. It's not very pronounced here because this is lower surface area than this, but it works with either end. And that's why we call it symmetrical synergy, for a catchy phrase word. And I know that Sergio Fuentes is in the room here. There's some nice micrographs that Sergio took. As a matter of fact, I'll use this one because it's got his name on it. And in the center of that phase diagram are blocks of cobalt and molybdenum sulfide. This area in here is the cobalt. These two phases interact at the surface, just as we said that they would in the electronic calculations. But what is different, which hasn't been recognized, is in the same way, this being the cobalt sulfide, this being the molybdenum sulfide, the evidence is that the excess sulfur at the interfaces is replaced by carbon. And then when we think of how these phases, the active sites of these phases, we have to think of something like this. Or if you want to think of it in a symmetric way, Gary, I'll let you think of the acronym and you reverse it the other way. That a lot of the conflicting data in the literature becomes clearer when you realize that when you're looking at the active phase, you're really looking at a sulfide-supported carbide. And I just end by thanking you, John, for really creating the environment that allowed us to do that. Thanks.
Any questions for Russ? Al?
Russ, in this type of system, is there a good adsorbate molecule to use to test to make sure there's certain size?
Yeah, well, what I think we came to the conclusion was that we very carefully calibrated the dibenzothiophene reaction itself. And we did that with microcrystals where we knew the surface areas. So they have to try on various gas absorbates and so on. We concluded that by calibrating the reaction, we could measure exactly the edge area and so on. So I think that the model reaction is the best program.
But are you saying there is no good probe for those sites?
Well, if you're thinking about a gas, the reacting molecules absorb, right? But if you're thinking of a gas probe, no, I don't think so. I think that most of them react topotactically. And there's been a lot of dispersion knowledge by, sometimes the oxygen will go in maybe 10 layers, and even maybe NO, so that most of the studies that you see in the literature will tell you that the cluster size of conversion patterns is 10 angstroms. We know that's wrong. So, yeah, I guess the answer is no, there isn't a good one that I know. We use the reacting molecule directly.
Thanks again, Russ.